second session for the day, which will be mainly about quantum materials and devices. And this is a very fascinating topic where it has kind of raised questions both in from the fundamental viewpoint and also very interesting questions from technological implication viewpoint. And we have a wonderful panel to talk more about all these aspects. So I request everybody to just kind of settle down so that we can have our committee members on the dais. Professor Ramkrishnan, Mukul, Aparna, and Atikur. And we'll have also Srijit. So we'll have a very kind of interesting discussion. As I told, this is a topic of interest both from a fundamental physics viewpoint and technological implication, and also closely related to some of the things what will be discussed in this session is connected to something what will be discussed towards the end of the today's conclave, which is quantum tech and quantum science and technology. And it's a very well-going field, and you'll find very many fascinating questions related to all these topics. So with this introduction, I will hand it over to the panel members. So I request you to also actually have sufficient time for questions, so that if we have about 15 to 20 minutes for the questions, that will be great. Because a lot of our students might be interested in asking questions. Yeah, I'll do it. Yeah, definitely I'll do it. Thank you very much. Yeah.
Good morning, everyone, and thank you, Pawan and his team to put together this nice show. Okay, so basically, this is a session for quantum materials. You can rename this session also as condensed matter physics. Okay, so what question comes first to the mind that, like, why some people call some material as quantum materials, okay, and not others. Okay, so the first this question appears because you take every piece of material, and in every piece of material, atoms are held together by electrons, okay, and electrons are quantum object, okay. So by that argument, every material should be quantum material. So then why this classification? Okay, so this is not, there is no clear divide between what would be called quantum materials and what would not be quantum materials. Let me put forward some of my argument to this, okay, that at what point you can call a quantum material, or a material which you might not perceive as quantum material, some properties might be of quantum effects. So basically, although it's all about electrons, materials are mostly all about how electrons talk to each other. There are a lot of phenomena, okay, which can be understood classically also. Although they appear from quantum mechanical facts, they could be understood classically, semi-classically, okay, or you can treat electrons as free electrons, or you can treat electrons independently, okay. So in those cases, or on those phenomena, I will not call them as quantum materials, okay. Also, I add something to this. If something is describable by quantum mechanics 101, let us not call that as quantum materials, okay. So then, what are quantum materials? As I said, that independent electrons or free electrons, even if you are treating them as quantum mechanical objects, are not quantum. So what you need to have a quantum mechanical effect is that strong electron correlations. So that means, like, where electron doesn't work individually, but they collectively work, okay, and that's why these electron-electron interactions become very, very important. So that's what I call as a strong correlation, okay. And then there are certain things which emerges at the macro scale. Okay, I can give you a view that, like, your water molecule, you can describe it by quantum mechanics, and you may know every property of a water molecule, but how it becomes a snowflake, okay, that's a kind of cooperative phenomena of many, many water molecules. Okay, so it's a macro scale emergence of that. And then the topology of quantum wave function, okay, is also wherever it is, it becomes important, you call them as quantum materials. Okay, this could be understood a little better by a very, very simple looking Hamiltonian. So let's say I have a lattice. I don't know if you can see this. Yeah. So let's say I have a kind of lattice. I don't care what structure it has, but let's say every lattice has 1 electrons in it. Okay. So these electrons can move from one lattice to another lattice, and that is your kinetic energy of the electrons. So this part of the Hamiltonian gives you the kinetic energy, okay, which is like you are treating it quantum mechanically, but if you only take this term, I wouldn't call those effects as quantum, okay, because it is independent electron. So now, what is important here, once electron goes and hops to another site, and if it sees another electron there, okay, and if that interaction is very, very strong, okay, that is your Coulomb interaction here, and this is very, very important for quantum mechanical effects, okay. And so this is, many of you might know, this is just celebrated Hubbard model, okay. You can extend this Hubbard model by putting a strong spin orbit coupling into the picture also, okay. And that leads to, so in this model I have kind of 3 parameters, kinetic energy, interaction, and spin orbit coupling. And you can kind of draw a very, very complex phase diagram depending on what is your strong electron correlation and how much you have as spin orbit coupling, okay? And depending on the strength of electron correlation and spin orbit coupling, you get exotic, you get many, many exotic quantum phases. It starts from topological insulator to wild semi-metal, axion insulator, Mott insulator, some are quantum spin liquid. These are some of the examples, okay? And none of these phases you would be able to deal with if you have free or independent electrons, or classically or semi-classically, okay? So then give me another example. Let's say like if I have a piece of metal, okay, I probably would not call it a quantum material. However, if that piece of material is showing me superconductivity, then superconductivity cannot be explained classically, okay? So it's a quantum mechanical effect only, and that appears from very, very strong correlation and interaction with electron phonons, okay? So all these things gives rise to very exotic physics in condensed matter physics, which is like dissipation-less and quantum dissipation-less transport, as you find in superconductivity or in quantum Hall effect, okay? You also get quantized transport, okay? Srijit is an expert of that, okay, which is again quantum Hall effect. You also get lot of exotic quasi-particles, okay? What are quasi-particles? It's at the end of the day, material has only electrons and electron-electron interactions, okay? And due to various different types of interactions, okay, electrons dress up differently, okay, like a clown, okay? So it's a electron, but it gives you exotic quasi-particle excitations. And to name a few, you can have Weil fermion, you can have Majorana fermion, you can have Dirac fermion, and all these things. And also you know that magnetism, although it appears from quantum mechanical origin, a lot of it could be explained at the end of the day classically also. Okay? So, however, there are some quantum magnets which cannot be described classically due to its long range entanglement and all this, and those are called spin liquids. Okay? So, basically, this kind of sums up some of the exotic physics here, which is quantum Hall physics, high TC superconductivity, and the quantum Hall physics would require quantum topology, okay? And high TC superconductor would need strong correlation, okay? That is exactly what I was trying to say in the earlier slide. And then there is Bailey phase, new particle fractionalization. This is quasi-particles, and there is plethora of exotic physics you get out of it, starting from multiferrics, spin Hall effect, topological insulator. You can use them to do use in quantum simulators, spintronics. So there is a lot of applications in future quantum technologies, starting from topological electronics to quantum computation to modtronics, designing new and high temperature superconductors and all this. So this is kind of some use cases where you would be able to use this. And so finally, if you want to take home one picture that is here, that electrons has various degrees of freedoms, okay, which is like, which orbital it lives, okay. It has a fundamental charge, it has a fundamental spin, and now you can add a quantum topology to it, okay. And so you can combine all of this together, okay, and then also it can interact with the underlying lattice, okay. So this gives a fertile ground to understand new and exotic physics, and that is kind of a broad definition of what quantum materials are, okay. So this is, so anybody wants to add anything on this? Or maybe later? Okay. So then I'll briefly tell you what our group does. So we basically do quantum materials modeling, okay, where we take strong correlation, add spin orbit coupling, sprinkle some topology into it, and sometime we also let our electrons interact with the phonons, okay. And one of our thrust area is to understand 2D magnetism, okay. And you might have heard a celebrated theorem called Hohenberg-Marmin-Wagner, which says that, like, there is no phase transition in 2D or 1D, okay. And basically the assumption to that conclusion is that if you take an isotropic Heisenberg model, okay, let's talk about spin system. So if you take an isotropic Heisenberg model, okay, then your spins can rotate in any direction, okay, without paying any price, okay. That means without paying any energy, okay. If that's the case, okay, then what happens if I have, so I have isotropic spins, my continuous rotational symmetry is there, as the spin has that, okay. And then what happens, if you are sitting at one magnetic configuration, you can rotate your spins to go to an excited state without paying any penalty, okay. If that's the case, then the system will not order at any finite temperature, okay. So that's why it says, like, there is no phase transition in 2D, okay. However, if you break that isotropy of the spin and add some anisotropy to it, okay, then you can no longer rotate freely, but you need to pay a price, okay. And that's why, one should gate magnetic ordering in 2 dimension, okay. For students, you might know that Ising model in 2D orders, right. So when it says like there is no ordering in 2D, you should ask that that's not correct. I know that Ising model orders. But when you take this realistic model, and if you put this anisotropy, which I said breaks the isotropy of the spins, okay, it becomes a Ising model, okay, at anisotropy to infinity, because you only have two directions up and down. But in real material, what happens, okay, which was first discovered in 2017, okay, is this anisotropy is very, very small, okay. And since this is very small, that means your penalty, energy penalty would be very, very small to go from your ground state to an excited state. So that means your magnetic ordering naturally happens at a very, very cryogenic temperature. Now, if you want to use that technologically, okay, you need to crank up that temperature to room temperature. So one of our agenda is to how to achieve high high temperature magnetic ordering in 2 dimension. Okay? And the approach we take is by manipulating the known system by external perturbations. Okay? And we have some success in that. Okay? Also, you can take another approach and you can design new materials or new platforms. Okay? Now, as I said, that they have a cryogenic temperature because your anisotropy is small, and anisotropy comes from the spin orbit coupling. So natural designing principle would be if you can crank up spin orbit coupling, then probably you can also crank up the TC. Okay? And that is one of the approach we are taking at the moment, that find out materials or take materials where spin orbit coupling is higher. So other than this, when we have magnetism, we also like to sprinkle some topology into the same system, okay? And these systems show very, very exotic properties to the tune of gives you giant anomalous Hall effect. It also gives rise to very exotic quasi-particles, and one of them is axion insulators. Again, this axion is a quasi-particle here, which traveled from high energy physics to condensed matter. Okay? And you can also engineer a dissipation-less current, which is also quantized in the form of quantum anomalous Hall effect. Then we also, what we do is we marry magnetism with superconductivity, and you know that they don't like each other, okay? And when you bring two people together who doesn't like each other, something exotic might happen, okay? And our goal is to hear whether we can design Majorana of fermions here, which may be very, very useful for fault-tolerant computing. Except that, we also let our electrons to interact with phonons to study superconductivity. We also like look into how phonons talk to other phonons to study thermal transport. Okay? And at times, when we are bored with everything of all this, we also try to understand light matter interactions in two-dimensional materials, which is not very easy to do, and we model excitons. Okay. So this is what we do as a group.
Yeah, so I think after the nice general introduction by Mukul on quantum materials, I'm going to skip this slide. So here I have listed some of the interesting quantum materials which show superconductivity, topological insulators, graphene, Weyl semimetals, quantum semi-liquids, and so on. So I will directly jump to one of the quantum material, which is superconductivity. So I'm going to skip all this and then go to superconductivity. So that is the area which I worked for more than 45 years, and it is strange that when I started this work at the Tata Institute of Thermal Research, I found that I was the only guy working on experimental superconductivity in the whole of the country. So it required setting up cryogenic facilities. You know, you need to set up a cryostat, works down to 1.5 Kelvin to room temperature. Both all transport, bulk properties have to be done. So it took a lot of time for me to build the lab. So it turns out that what we did in late 70s and early 80s were superconductivity research related to some A15 compound, then the high TC superconductors and so on. And then finally when I retired, that was the only lab which was working at microkelvin. So for reasons which I will try to tell you. So superconductivity is a ubiquitous phenomenon. If you look at the periodic table, nearly 2/3 of the elements are superconducting one way or the other. Okay, so there was a beautiful theory which is called Bardeen, Cooper, and Schrieffer in 1957, which showed how the superconductivity can arise in conventional metals. The theory was so beautiful that it clearly deserved more than one Nobel Prize, if you ask me. It also predicted energy gaps and so many other things as well. The one thing which it's failed is because it gave a relation for TC, and the experimentalists jumped onto that and tried to find new superconductors based on this. What they forgot was the important part of that theory is to show how superconductivity can come by attractive interaction between the electrons. They didn't bother about what is happening in the real solid. You have unharmonicity, you have complicated Fermi surface, you have defects, you have disorder, so many other things. They didn't want to do that, correctly so, because they just want to show how the superconductivity arises. But then they made a mistake of giving an expression for TC. And then people misunderstood. Even great physicists like Bernard Mathias, who had discovered thousands of superconductors, were extremely critical about the theory. It is just that the theory will not be applicable in those days to all the conventional superconductors which have so many difficult problems in the system. Of course, in the last, let's say, one decade or so, things have developed, computation has improved. Mukul can clearly tell us what the superconducting TC close to experimental thing in conventional system. So then what are the current ideas of superconductivity? So you can see that how complicated it is. You have phonons. These are quantized lattice vibrations. They are excitations. And that provided the glue for conventional superconductors. Even there were problems, because how does two electrons get attracted? They are Coulomb repulsion, right? That will not give you attraction. What happens in the solid when the electron moves? Physically, you can imagine this way: there is a positive cloud created when it moves there. The other electron, which is coming after some time, gets attracted to this cloud. The ions move at a very low velocity compared to the Fermi velocity of the electrons. So they can't relax back before the next electron comes. So it's called the indirect interaction, which gives the attractive interaction between the two electrons. This works if you know that atoms vibrate in a small velocity as compared to the Fermi velocity. What happens when you have the characteristic energy, which is the Fermi energy comparable to the lattice energy? Then this picture breaks down. So the first one, where the Fermi energy is much larger than the lattice energy, it's called the adiabatic approximation. So this breaks down in a system where you have lattice and thermal energies are comparable. So this is why we developed a microkelvin fridge and looked at bismuth. If you look at the periodic table, bismuth is the only element where you have Fermi energies comparable to the lattice energy. So do they show superconductivity? Yes, it shows, but it shows at 500 microkelvin. So, but then the mechanism for superconductivity there is different. So you have adiabatic, non-adiabatic, non-phononics, cuprates, heavy fermions, topological superconductors. Then you have ion-based chalcogenides. Earlier, magnetism is thought to be determinant to superconductivity. You don't find any magnetic superconductors in the earlier time. People have now seen there are a large number of ion-based, magnetic-based superconductors, and In some extreme cases, like uranium, germanium 2 under pressure, the residual magnetism is important for superconductivity. If you kill the magnetism, you kill the superconductivity. So things have been, changing in the last 45 years. I have seen many new things have come, many new interactions have been brought. The important aspect of this is every new discovery of superconductors bring new concept of physics. People talk about high TC. The high TC oxides is a paradigm shift in the study of superconductivity. But it's not high TC alone. The high TC brought new concepts in physics, like marginal Fermi liquids, whole new understanding of what is happening in the condensed matter system. And this high TC then brought the understanding of colossal magnetoresistance. Many of the other things have come. Now the latest addition is these topological superconductors. They are superconductors, but their band structure is completely non-trivial. They have band inversion, all kinds of things are there. And then I think Mukul said about Majorana excitations and so on. Please remember, when solid state physics talk about Majorana, that is different from the particle physics or the nuclear physics talk about Majorana. They are talking about individual Majorana particles. For instance, nuclear physics, they have been struggling to find this Majorana particle using neutralized double beta decay and so on. Here, we are talking about excitations collectively behave as a Majorana system. Same thing for the other excitations which you see, wild fermions, which was discovered more than 10 years ago in tantalum arsenide. So the sum of it is quantum materials are extremely interesting. Their use for the commercial applications is still not, at least the topological material is still in the offing. Probably soon that will get realized. In my recent effort is we are trying to look at high pressure superconductivity. People have seen at 250 Kelvin in lanthanum hydride, but these are under extremely large pressure, something like 1.5 million bar. So what one wants to see, can we get it at slightly lower pressure, at least in the ambient pressure? Then you have these low carrier systems, which are not expected to be a superconductor. Bismuth is a prime example. Then it happens in strontium titanate, for instance. If you remove one oxygen from there, it would start superconducting at millikelvin. Then we have this boron addition to quench condense carbon, which is reaching up to ambient pressure at 55 Kelvin. And there are interplay of superconductivity, magnetism, charge density wave, where you would probably get into unusual states which may or may not find any technological applications. The last one is the very important discovery. I think Atikur works a lot on tungsten disulfide. There is a monoclinic version of it. 2 layers of that is showing unconventional superconductivity, where they have zero energy bound states called the Majorana states in the system. So I've been looking at some of these. You must also important that my lab facilities are somewhat limited, but I'm still collaborating with various members here as well as outside to understand this intricate aspect of new superconductors. I would like to stop here and invite Atikur.
So I was here yesterday when I talked a bit about what we do in the labs, in my lab, and one of the verticals I said is looking at strongly correlated materials. Mukul did give a very good introduction about what we mean by a quantum material. Recently in ACS, American Chemical Society Chemical Reviews, there was a very nice definition which I personally liked. So quantum material is the one where classical particles or calculations that do not take into account the full character of the system, do not adequately describe the electronic or the magnetic properties displayed. This, it's a personal favorite. This is the best definition, I think, of quantum materials. What we do in the lab, our primary tool of investigation of any material is the scanning tunneling microscope. And at the risk of being tool specific, I really want to tell you that if you, there are many nowadays instruments that give you pictures of atoms on of the surface. But now when we talk about correlated phenomena, where for example, one is charge density waves. So there are electrons, and then sometimes the electrons in some cases they talk to the lattice, and then they couple with the lattice. There are, and this manifests as some extra modulation of charge density. Okay, so I have just this one STM image. If you see the red areas, where you see there are brighter dots which are further spaced, and then there are smaller lighter dots in between those two fatter bigger red dots. The point I am trying to make is, this is a real space image, okay, of this real phenomenon, a correlated phenomenon that is happening in a particular material called titanium diselenide. Okay. The inset shows a Fourier transform. Now when you take the Fourier transform of just a periodic lattice, you see the lattice points. Now inside the outermost hexagon you see extra peaks. Now these extra peaks tell you what other physics is happening in the system, what other interactions are taking place, what other quasi-particles are contributing to the physics of the system. And one of the very interesting, very rich in physics system is the Kagome superconductors, which are compounds of vanadium, Sb, which is I am blanking out, AV3Sb5, A is where A could be either potassium, rubidium or cesium. And if you check the schematic, there are all kinds of exotic phenomena, some of which can be studied with the scanning tunneling microscopy and spectroscopy. And we are currently looking at CSV3Sb5. We get our samples from Luminitsa, who is really a magician. A crystal grower is really a very mild way to describe her. She gives us the crystals. We have a collaboration with her. And see, many times at the end of the day, you are trying to study nature, how nature manifests in materials. For CSV3Sb5, now, which is supposed to be a nicely ordered surface, we see this picture in blue, where this picture in blue, where instead of this ordered structure, we also see some disorder. And this is the cesium phase of this crystal. Now, we are also trying to understand why this is happening. So, the point being, especially in this area of work, sometimes you have fixed ideas in mind that, okay, I want to see superconductivity, or I want to study CDWs or some other phenomena. But sometimes you also end up seeing things which make you go back and ask the question, or ask a newer question as to what exactly is happening. So in short, quantum materials are interesting, exotic, and sometimes they might themselves have some surprises in store for you. Thank you.
So in our lab, we study, yesterday I told about some advanced materials and related stuff. Apart from that, we also do, say, some work on quantum materials. Okay, less materials, more like, studying their properties. Some quantum materials that we grow or we are interested is these oxychalcogenides, tellurine, some TMDs. And nanoparticle, I put it here, quantum materials, because they may not be quantum materials in that sense, but their properties, okay, when you put in a collection, okay, there are some quantum phenomena that emerges, and that helps in your ultrasensitive detection. So it's kind of more towards quantum sensors. So this is one bismuth oxyselenide, this is few layer. These are not van der Waals material, these are non-van der Waals. But the advantage is that this is damn stable, okay, as it's basically Bi2O2AC, it's a oxychalcogenide. So once you grow them, it's perfectly fine. The advantage is that it has a very high mobility, so people are kind of getting very interested. I think it was discovered in 2019 or 17, something like that, not too long ago. Okay, and the mobility seems, now gone, I think, more than 1 million or something. Okay, so the only other material that you can figure out is graphene. The advantage is that it has a small band gap. Okay. And the other biggest advantage is what people recently found, that after growing this material, if you do some post-processing, okay, you can make a very thin layer of oxide on top of it. The reason silicon is still the champion and probably rule another at least 30 years, that's what I believe, is because silicon has a native oxide, it has large abundance, you can easily synthesize them at a unbelievable purity. Right now, I think the purity level is 1 impurity in 1 billion silicon atom. Okay, it's so pure. I think the mean free path is kind of reaching to more than millimeter. So this is another upcoming kind of rising star, and what we found that by tuning the gate voltage, basically by tuning the carrier density, because as Mukul said that it's basically the interactions that leads to some material to quantum region. So when you change the carrier density, you basically tuning the interactions among them, and we found that you can go from a metal-like state to insulator-like state. Okay, I should not say that metal insulator, it's metal-like behavior. Okay, to a insulating type behavior. The other material that again, this is a TMD. It's basically MOS2 that is somewhere. I don't think you can see it, but these black outlines are basically graphene lead. So most of the time when we make samples, okay, we put the gold chromium leads or titanium gold or palladium gold kind of lead or platinum leads. But a lot of time it's basically kind of fabrication challenge. And what we found that if you place a contact material which is van der Waals type contact, which is making a contact that is van der Waals type, then the properties is slightly different. So basically what we can say that when you are studying these devices or the quantum material, especially at nanoscale, contact is playing a big role, and you should figure out that you are studying the bulk property, not the contact property. And here what we found that when you are changing the carrier density, again we are increasing the gate voltage. Initially it was insulator type, but then as you are increasing the carrier density, you are seeing a metal-like behavior. Okay, and this point, that you can tune based on what is your carrier density in that system. But if you make this sample with just chrome gold contact, different type of contact, which will give you a Schottky type of contact, then you may not see this phenomena. You will always see insulating type behavior. Okay, so to understand the intrinsic properties, you need to kind of also do a little bit of contact engineering, you can say. There are 4 probe measurements also, you can make 4 probe, but there are also problems with that. So this is another material, this is tellurine, few layer of tellurium. The ultimate aim is to get a monolayer of tellurium. Here also you see a metal insulator type behavior, and again what we believe is that the contact is playing a significant role. Because if I increase the distance between these contact pads, then I don't see this insulating type behavior. That still we believe, we are not sure, we are doing some more measurements to understand that. So basically the quantum properties that we are interested is mainly driven by the carrier density or basically the interactions. We are tuning the interactions, at the same time the disorder. So basically interplay between disorder and interaction. Now, device fabrication, this panel is supposed to be quantum material and devices. So I'd like to just say a few words about device fabrication. From yesterday till today morning, there are various panels, and what you can figure out that ultimately we need to make something to realize, for particular applications. Even Seema was telling about the new detectors and all those things. So this all comes under the fabrication. You talk about all sorts of platforms for quantum computation, ultimately it boils down to fabrication. Okay. So how you fabricate, whether it is superconducting qubits or it is ion trap based one, it is photon based, everything you need to make device. And we do little bit of research on device fabrication because we are bound to do that. Without that it's kind of impossible for us. So here one example of a crystal. This is a slightly different type of crystal. It's CSP BBR3 two-dimensional crystal. The problem is that it is water soluble, so you cannot do the conventional lithography. So we developed a new lithography technique through which you can do the metal deposition or photolithography using on a water soluble material, okay, which is kind of a good achievement. This is another one. This is a TMD layer which you cannot see. It's underneath this HBN, hexagonal boron nitride layer. So here we actually made a van der Waals contact. So basically it's again a field effect transistor type geometry. It has a gold contact, but the gold contact is not deposited on the material, rather the material is transferred on the prefabricated contact, and that can give you a van der Waals type junction. So basically the electrons will now tunnel and you'll get a very low contact resistance. And here what we found that once we make a top gate, the mobility that we are getting is kind of reaching the theoretical mobility of MOS2. Theoretical mobility is 400 centimeters per volt second, and what we are getting is 385. Okay. So it's again because of the device fabrication challenge. And here, Professor Ramki said about this twisted layer, the new superconductor, not only the superconductor, a lot of other phenomena that you see by placing one graphene on top of another one at a particular angle, and that gives you all sorts of interesting phenomena. Basically, that's a very important test bed for various quantum phenomena. Some of them we still don't understand, we're trying to explain. So we recently developed a technique where actually transferring graphene is easier, but when it comes to TMDs, they are a little bit tricky. Okay, their bonding with the substrate is much more stronger. We don't know why. Okay, but we came up with some technique. It's kind of a bit clean one. So we say it all dry technique. There is no solvent involved in this technique. Okay. So now we can place one TMDs on top of another. All are monolayer. Okay, and we can kind of control their
question and answer. We have to now get into the question.
So yeah, we can probably control them. And this is the last one. So here you can see this is kind of big piece of glass coated with silver, and then this we have we thermally deviated, so we made nanoparticle. This also is the nanoparticle. So you see the visual color difference, and if you see it under ACM, you will see that the particle size is largely different, but here the particle size is smaller, and there's the density is very high. The only difference was done is that the de-weighting is done in a confined environment. It's supposed to be a very simple thing. I was kind of surprised that why people didn't explore this thing. Okay, so the patent is, it's a pending patent. So we'll see how it goes. Thank you. We'll start taking the question now.
We'll switch over to the question answer session because we'll have about 15 minutes. So students, please do ask questions.
Professor Atikur mentioned that the different types of contacts, Schottky and van der Waals. So I wanted to know what are the differences between them, and like how are they suppressing the metal like to semiconductor like transitions. These observations.
Okay, Schottky contacts are basically metal semiconductor contacts. Okay. If you measure the IV characteristic, most of the time it will give you a nonlinear IV characteristics because they are rectifying behavior. But sometimes it's a little bit difficult to figure out that it's a Schottky contact, because if you have the same metal on both sides, okay, you will have kind of a back-to-back diode, and depending on how much voltage you're applying, if you're applying a very low voltage, you can still get a linear behavior, and it apparently it might look like, okay, we are in the ohmic region. Okay, so one way to test them is to reduce the temperature. Okay, you go to low temperature, and if you still see that it's a linear IV characteristic, then hopefully you can kind of safely say that, okay, there is ohmic contact. Okay, so this kind of material, most of the time they show nonlinear IV characteristics, or maybe in the low bias, it's still a linear IV characteristic, room temperature. But once you go to the low temperature, then they will start showing the nonlinear behavior. But if you make them with van der Waals contact, especially graphene and other materials, okay, there it will show you linear IV characteristics. It's mainly because the tunneling is there between those contacts, and the effect is much less. So you can probably study the sample's intrinsic properties rather than the contact dominated properties. Actually, the tellurine is slightly different. We still don't understand. It seems like the contact is inducing some metallic states into the material. We found one theoretical prediction which was done quite some times back from IISc, and no one probably paid any attention to that. We are still kind of, we should not say that, okay, we found that, but there is a signature, and we are trying to figure out whether that is the case or not.
My question here is about actually supersymmetry. Does it occur as some sort of interesting emergent phenomena in some materials? And if yes, does it lead to any interesting technological applications or something?
No, and no. So, okay, my general opinion about trying to think about condensed matter ideas in templates of high energy physics is a bit negative. But there are tools from field theory that do get applied in any many-body system. So you may see ideas that may have already been seen in other contexts. But as far as and therefore axions and Majorana and things like that, critical phenomena. But as far as supersymmetry is concerned, the idea of supersymmetry has been used in certain contexts very early on by Wegener to understand localization and things like that. But as far as a particle or some concrete experimental evidence, I don't believe there is anything meaningful.
So I just wanted to ask him about the related question like this. There has been a lot of talk about, string theory and the connection towards the condensed matter and so on. And many of the condensed matter, especially on non-Fermi liquids, our understanding from the theoretical side is rather poor. These are for the audience. Generally, metals have what is known as a Fermi liquid properties. Their electronic specific heat goes as linear in temperature. They do show in the resistivity as T square. When the high TCs came, even before the high TCs came, heavy fermion systems, some of them behave not as these Fermi liquids. They call it collectively as non-Fermi liquids. They have divergence in many of the properties and so on. It's still not understood from the rudimentary condensed matter many-body theories. So my question to him is that there's strong connection apparently by the string theories and the certain aspect of the condensed matter. Does it help to understand this non-Fermi liquid from this connection?
Yeah, I'm not an expert on this, but I can first tell you what the context is. So it turns out that I think Ramki had mentioned this. The simplest superconductors are sort of understood why things superconduct. The mechanism is the phonon, but the phonon-based superconductors have you can show that the TC cannot be beyond a certain point. But experimentally you see plenty of superconductors whose transition temperatures are way above this limit. So a mechanism is not known which can explain why these things superconduct. You find one, you'll not immediately, but definitely get a Nobel Prize. But there are some things that have been noticed about these superconductors. There is a proximity to some kind of ordered phase, typically a spin ordered phase, an antiferromagnet nearby, and that sort of suggests that the superconductivity might be happening because of some fluctuations in the case of the simplest superconductors, the superconductivity is happening because the electrons couple to some fluctuations of the ion, the phonons. But in this case, since there is always a proximity of an antiferromagnetic order or some kind of spin order, the guess is that there is some kind of coupling of the electrons to these fluctuations of the antiferromagnetic order. If you put these together into a theory get rid of everything else, you have fluctuations of the spin order and the electrons moving in the background of these fluctuations. You get a theory which is too strongly interacting to be solved by any simple techniques. We have been hearing about how non-perturbative things cannot be calculated, cannot be solved, and this is one classic example. Again, if you make progress, you'll probably get a Nobel Prize. So one scenario where there is a way out in some other context is through this gauge gravity duality, and people have made some attempts at taking toy models of these couplings between spin systems and electrons, and there are certain contexts in which things can be solved, or you can map this strongly interacting problem to somewhat of a tractable, integrable system, and that is the context in which this we now have a lot better set of tools to study interacting systems, but in terms of explaining the thing that we wanted to explain, we are still nowhere. Yeah, so that's a somewhat broader summary.
I wanted to ask about topology. So theoretically, we have a very straightforward definition of it. You calculate the, you can define it. You calculate the wave functions and you then calculate invariants. If they are non-trivial, you call it topological. But experimentally, do we have anything concrete that, okay, if we see these observations, we can call these topological materials? And second question, when we say something is like a topological superconductor or topological magnet, are these two things talking to each other, or is it just does topology add anything to the superconductivity of it, or is it just this particular material has topological band structure and shows superconductivity?
Sounds like there are three questions there. Let me answer the easy one. You said there are concrete experimental evidence. I will put the, in case you're not familiar, or if you're familiar, let me remind you that this topological quantity was first experimentally measured, and then we found out that it was topological. Quantum Hall conductance was a quantity that was measured. I'll talk about it in the next session. You see that the quantum Hall Hall resistance, when measured, has an accuracy of 12 decimal places, I think 12, about 12 decimal places, and it is measured in an object that has nothing, no property that is accurate beyond the maybe 3 decimal places. So this has to come from topology. And this was first measured, so obviously there are measurable implications. There are many, many measurable implications in the quantum Hall context for various reasons. As far as, what was your second question about topological superconductivity? So there are concrete predictions about what may happen if there are topological superconductivities. The Josephson effect, for instance, would have a different behavior. Ramke may have more concrete things to say about that, but unfortunately there hasn't been any discovery of topological superconductor.
So the thing which you mentioned about the topological superconductors, one of the powerful technique is to look at angle resolved photoemission, which maps a Fermi surface, which gives you some energy of the gaps and so on. What is known about these topologies? They have non-trivial band states. Okay, and there are some experimental evidence that you have what is called the Majorana excitation with zero energy gaps and so on and so forth. But as Sujit said, these are ongoing problems, and what is shown in one group is heavily contested by another group. But the observation of these non-trivial bands and Fermi surface, Fermi arcs and so on with angle resolved photoemission is true. That is an experimental evidence. But what is the consequence of that is still debatable. Okay? It is predicted that these kind of superconductors, let's all, there is a claim that people have made these bound states of Majorana excitation with zero energy and so on. People have claimed, even this new Microsoft thing which you must have heard, this Majorana, if you can really stabilize and have a zero bound state, they could have a quantum computing. They are tolerant-free quantum computers. So Microsoft has just put up, you must have seen that. But it's still, people have not confirmed that there is a Majorana state exists or not. It's still a questionable thing. But as I said, I have infinite faith in the quantum physicists and the quantum engineers. Things would come up. Maybe it takes time. I will just give you a very nice example, which is a very old example. Camerling owners found superconductivity in 1911 in mercury. It took 60 years to find the application of a superconductivity. In 1971, the superconducting magnet came. And today, you go to any hospital MRI, you cannot avoid a superconducting magnet, right? So took a long time. I must say that those days things move a little slowly, but the transistors came very fast. Things are happening at a much faster rate, but the applications really will take some time, and then to really prove this phenomena, it's going to take some time. See, for instance, high TC. When the high TC came in 86, I was just finishing my PhD at the time. For nearly 1 decade, you have all kinds of experiments with not so high quality samples, and the theoreticians are really confounded by it, because somebody says TC is 100K, then you found that the calibration is not correct, and so on. So it can be as problematic as when the new development happens. You need to wait till things subside, and then high quality samples come. Then, really it brought out emergence of new physics. And what is important is that these are emergent phenomena. The constituents may not have that phenomena, but when they combine, they come out with some new phenomena. And that keeps happening in condensed matter all the time. And the applications are not far off. I think it will come, but it may not come on the shorter time scale. We need to wait till things are settled, and then it will come.
Yeah, there's one.
Yeah, Ramki, your comments have inspired me to make a little comment of my own. All the ideas which are somehow lying in the future right now, like realizing Majorana fermions in concrete way, or any other understanding non-Fermi liquids or whatever, there are two approaches that a scientific community can take, and I was very happy to hear you take the second approach, but the first is more common. The first approach is, it has not been proved. We are not going to do anything till we are going to wait and see, and somebody should do it, and we won't believe it till then. Second approach is, let's believe that it's going to happen, and let us try to do it. Let's jump into that. And I feel, it's my comment in view of my advanced age, I think our community is poorly attuned to getting into risky topics. It is risky. People might never find this Majorana fermion. And our funding agencies are also poorly attuned to supporting risky topics. If you had applied for a grant to study AI 20 years ago, it would have been turned down. But people were working on it in the West. The explosion came from the West, didn't come from us. Why? Because we would have not been supported to do it. So just a little comment that maybe we should think about.
Yeah, I just wanted to echo the same thing. When I tried to look for the superconductivity in bismuth, lots of people said, no, it's not going to do that. It is only 5 orders of magnitude. Because you see, you need large condensed electron carrier constellation to see superconductivity in conventional theory. But this is 5 orders of magnitude. And then I proposed to my student that, can we look into it? There is an interesting part there. So he asked me, is there a backup backup experiment? So I said, don't worry, your backup thing will go on, but let's work on this. So that took us about nearly 3 years or 4 years after the microkelvin fridge was set up. Then once we found superconductivity, there were lots of theories, including, I remember Gorkov, before his death, he wrote a long email to me that, this has been, I have been thinking about it for a long time, and then I'm happy that this has been discovered without this one. Gorkov. That was before his death. Then Phil Anderson did have a long chat with me, and Phil was always interested in bismuth. for the reason why I told you that bismuth is one of the only element which has 5 orders of magnitude in electron concentration. It acts like a semi-metal. And bismuth has been studied for 120 years or more than that, because it showed the strong diamagnet in the elements and so on. So he himself was interested and said that don't worry, it is low Tc, but it is important that it is superconducting. So that was his last statement. So the point which I am trying to tell you is that don't be afraid. I think you plunge your hand, experiment is experiment. It probably requires a development of certain experimental techniques which is required for doing this. And don't be afraid, just plunge in, make your hand dirty, and something good will come out of it in the long run.
Wonderful. So, quick question.
Very nice interactive session. Just one quick comment and one quick question. Quick comment about, as Srijit said, he was very negative about the application of ideas from across the sector. I think that's one attitude.
I wasn't negative. I was making a factual point that so far nothing has become.
Yeah, no, I agree, but there are a few exceptions. Like 3D IC model, critical exponent, I think that is the best known by a bootstrap method rather than any other method. So I think rather than becoming negative, as we have learned, becoming positive, because across the discipline, theory discusses with experiment. That's the kind of thing would be much more useful. And as Sunil pointed out, being futuristic rather than what is established is much better to go ahead. One quick question would be, this quantum materials, all these things, how much theory people able to do rather than just simulations? That my general question.
So, like any other branch of physics, okay, so in quantum materials or / condensed matter physics, okay, so there are sets of people who should come together and work, and that is how the progress happens. So what type of people here is required is people who can do many-body physics, okay? Then people who can do computational condensed matter, who does kind of many-body physics for realistic systems, okay? And then you require somebody who can grow fantastic single crystals, because if you don't have good quality crystals, you cannot do good quality physics, okay? Period, okay? So you need that kind of people. And then you need people who can make devices, because as a theoretician, my perspective of device is twofold. A, not only for application-oriented devices, but if you want to understand physics, you need to first build a device, okay? Otherwise, what and how you would measure things, right? So any physics measurement would start with a good material and a device. So there would be a device kind of people, and then who does all sorts of experimental measurements. And all these people should come under one umbrella for the progress. Okay.
Just like the panel who have come together to talk about these questions, it actually reflects that we have people from computational theoretical physics viewpoint, hardcore experimental viewpoints, and it also kind of captures the essence of the physics very nicely. So, talking about the future, let's first and the foremost thank the panel members for this wonderful discussion. There is a lot more to explore. There are also multiple sessions which are actually subsequently lined up.